High pressure in the shielding gas delivery system causes problems of gas waste and inferior weld start quality. We'll show the benefits of high pressure in this video. Let's view the pressure in a MIG welding system when welding and then when welding stops. This is a view of a pressure gauge placed in the gas delivery hose. While welding, the pressure needed to flow gas through the feeder and the torch is 3.5 psi as noted. When welding stops, the solenoid closes, but gas continues to flow into the gas hose and pressure quickly reaches the regulator pressure of 25 psi in this case. The engineers designing MIG shielding gas flow systems knew flow restrictions occurred in production. Choke flow was used to automatically maintain the preset flow regardless of the flow restrictions that occur when spatter builds in the gun nozzle, the gun cable is bent, and for other causes. To deliver 30 cubic feet an hour of gas flow through the wire feeder and torch requires very little gas pressure, typically 3 to 4 psi, measured at the feeder inlet when the MIG gun nozzle is clean. However, in production, there are inevitable flow restrictions. Spatter builds in the MIG gun nozzle and gas diffuser. The small gas passage in the gun cable becomes bent and often doubles as the wire conduit and can clog with debris. These restrictions can cause the required pressure to increase to 8 psi. Flow rate through a given size orifice can be defined by the pressure both upstream and downstream using this fairly complex equation. When flow restrictions occur, shielding gas flow decreases when downstream pressure increases. Choke flow is used to maintain preset rates regardless of the restrictions that occur while welding. Choke flow relies on the fact that the velocity of gas in a small orifice or needle valve cannot exceed the speed of sound. Once that velocity is reached, the only pressure controlling flow is that upstream of the orifice or needle valve. Downstream pressure and therefore added restrictions have no effect on the flow rate. To achieve this condition, the absolute pressure upstream of the flow control device must be greater than approximately 2 times the downstream pressure. Applying this criteria to our MIG welding situation, we obtain the following. Assume the pressure needed at the feeder is an average 5 psi. That's 20 psi absolute. To achieve choke flow, the pressure upstream of the flow control needle valve or orifice must be at least twice that, or 40 psi absolute. To get back to gauge pressure, subtract atmospheric pressure, or for our purposes 15 psi. Therefore, the minimum pressure needed is 25 psi. It is no coincidence that the quality regulator flow meters and the regulator flow gauges from various manufacturers shown here operate at 25 to 80 psi. Few companies introduce low-pressure gas flow control systems in an attempt to reduce the gas surge at the start of a MIG weld. The following tests were conducted to see how much flow variation this approach creates. The flow is measured at the MIG gun nozzle with a portable flow meter, as shown in the upper right. Flow restrictions were simulated as if spatter had built up in the gun nozzle and gas diffuser. Gas pressure was measured at the inlet to the feeder to quantify the amount of restriction introduced. The measured results agree with the calculations made using non-critical flow equations. 2 devices were tested, a conventional regulator flow meter that employs a 25 psi regulator, and a low-pressure regulator surge-reducing device. This model is designed to mount at the MIG feeder. Initially, both devices were set to flow 31 CFH, and the flow restriction was set at 5 psi. The flow controls were not changed from that initial position for the remainder of the tests. Restrictions were then added and removed so the pressure varied over the range found in production, namely 3 to 8 psi. Looking first at the top row of data for the conventional regulator flow meter, note the initial flow rate of 31 CFH remained at that level for the full range of restrictions tested. Looking at the bottom row of data for the low-pressure device, set initially at the same 31 CFH with no changes and adjustments, flows varied from 16 CFH to 37 CFH as the flow restrictions changed. A huge difference. Of interest, the flow-calibrated pressure gauge read 31 CFH for all the different flows. That's because the regulator pressure was not changed, only the restrictions. A low pressure add-on device was also tested. Flow variations were even worse with this device. Where the previous device changed 4 CFH for a 1 psi restriction change, this one altered flow 8 CFH for that same 1 psi change in restriction. Note that some of these devices do not mention they use low pressure. They may just say they eliminate gas surge. A number of fabricators reported and quantified problems they found with low pressure devices. The 3 discussed here all use one that mounts at the MIG feeder, the same one we use for our tests. The first, an automotive OEM, installed 32 of these systems. After several months of use, they were all discarded. The welding engineer reported measuring significant flow changes while the flow gauge read the same preset level. He also said it was obvious there was insufficient gas at the weld start, creating inferior deposits. The second welding engineer spent quite a bit of time and effort trying to solve a weld porosity problem in one plant, making identical parts that another plant was producing satisfactorily. He found one of the key problems was the plant with a weld porosity was using this low pressure surge eliminating product mounted at their wire feeders. They were removed and the problem eliminated. When discussing our gas saver system with the third fabricator, a bar joist manufacturer, they were reluctant to try our system since a year prior they discarded 50 of these same low pressure surge control devices mounted at their feeders. They stated that the welders were always changing flows and complaining about the lack of sufficient shielding gas. From our tests, it's obvious they could have experienced a wide range of gas flows while the flow gauge read what appeared to be acceptable levels. The company did test our gas saver system for several months. After seeing excellent results, they installed them on all 50 welders. After a year in service, their gas supplier called to see why their purchases were down over 30%. Production hadn't changed. In summary, choke flow is used to automatically compensate for flow restrictions. However, this requires high pressure, which builds significant excess shielding gas in the gas delivery hose when welding stops. This excess is expelled at a very high gas flow rate when welding starts. The high flow wastes gas and causes air to be pulled into the shielding stream. A solution to these problems is to use our patented gas saver system and not low pressure devices that create their own problems. Just what is a gas saver system? This patented device uses a custom extruded small ID, large OD gas delivery hose with special end fittings. The fitting on the feeder end incorporates an orifice that limits peak gas flow at the start. Excess stored gas is reduced 80%. It does not set or control the steady state flow. It simply replaces the existing gas delivery hose. The gas saver system supplies a controlled amount of extra gas at the weld start to purge the MIG gun nozzle and weld start area. This provides superior weld start performance with less spatter. It does not alter the high pressure built in the MIG system since the invention of the process. Preset flow is maintained even with the inevitable production flow restrictions. The gas saver system has no moving parts to wear or knobs to adjust. Unlike other devices that have been tried to solve the blast of gas at the weld start, like low pressure or simple orifices, welders appreciate its benefits. Fabricators can typically expect 40 to 50% reduction in shielding gas use with the system. For more information about our patented shielding gas saving products, visit us at netwelding.com. That's www.netwelding.com. Thank you.